This video is connected to the November 13th remote session, in which we've been talking about advanced applications with raster processing. The first three videos in this series dealt with creating topographical surfaces. So we learned about LiDAR, we learned about the LiDAR point cloud, and we learned about how to turn that into an LAS data set so that we could create a surface of the Earth and then model that, figure out the slope, figure out how to connect the visibility analytics, and all of that. The next sort of practical based raster I'm going to teach you is a little more abstract. It's easy to wrap your head around the output of a topographical surface where each cell in the raster represents your elevation, and then taken together they form an actual surface of the land. The next tool I'll teach you is called density, and it creates something that's a bit more abstract. In this instance, each value in the raster grid is going to show you the number of a thing within a certain distance. Its density, its concentration, its intensity. The use of density is to create heat maps where you can show where things are clustered and you can show how intensely clustered they are. We're going to run this predominantly with two types of data. We're going to run it first with the crimes. So there was a data set of crime incidences in Philadelphia. And then after that, I'll run it with the crash data, which is a data set of where there were bicycle, car, and other automotive and pedestrian crashes in Philadelphia. And I'm picking these two different data sets to demonstrate density to really show how the inputs for this tool will dramatically affect the outcome and really change whether you're trying to identify concentration at a very narrow, focused, granular, intersection or street by street level, or whether you really want to show concentration and density at a broader neighborhood level. So those terms I think will become a bit more clear once we demonstrate the tool. So typically, right, it's like all the other raster tools, analysis tools, toolboxes, and you could navigate down to spatial analyst, and it'll be in the second data set, which is density. Now there are three different density types, but we won't learn any but kernel density. Kernel density is sort of the prime one that we'll focus on. So we'll open that up. So give it a second to load. So kernel density, it creates what's called a heat map. And that term heat map, it can also be instructive to help you visualize what we're about to accomplish. If I zoom in, because we're pretty far back right now, right? So it sort of looks like there's a mess of points. If I am looking to understand the density of crime in an area, I'm aware that there's a crime here and here and here and here and here and here. But what I'm not aware is if I were to pull back and try to visualize all of these blocks together, how intense is that concentration and clustering of crime, say, compared to something like here? And so the metaphor of a heat map works because you can almost envision every point giving off a certain heat signature. It's like some of them might be lighters, some of them might be heat lamps, some of them might be flamethrowers. And depending on the intensity of that heat would determine how far it travels. And so if I'm right here, I'm not going to be too hot, quote unquote. I have a crime here, a couple up here, so maybe there's some intensity a little bit more to the north. But overall, I'm not as intense as, say, this area right here, right? Right here, I'm between several sub-clusters and pockets of crimes, and so their heat would be radiating more and would demonstrate a greater concentration. I would appear to have a much higher number of crimes per square mile or crimes per acre. So in order to create this tool, you'd come up here to input pointer polyline. And this is important, right? You cannot do density with a polygon. And I'll remind you as sort of our last step in these videos of a tool we learned several weeks back where we can convert the form of vector data. So if we want to move from a polygon to its centroid, we can do that and then load it into a tool like this. But, so just know that, right? If you have polygon-based data you want to analyze and you want to determine the density of, you need to convert it to a point. This tool here, population field, is pretty important. When you're running density, there might be some instances where the point itself is representative of the incident. And that's true of crime, right? Each point represents one crime. So there is no population field. There is no attribute or piece of information that says this crime is actually 5 crimes. This point is 7 crimes. This point is 9. But that's not always true. When we run this with crash data, or later when we run it on the Philadelphia blocks, you'll notice that in those attribute tables, there is actually a piece of information that stores the number of crashes that took place at that intersection, the number of people that are in that block. And in that instance, the incident itself is not enough to create density. You need to be almost smushing down that population field, right? If there are 1,000 people living in one dot, but 1 living in another, that dot with 1,000 needs to give that full weight. It's far more intense. It has far more heat to disperse than the dot where only 1 person would live. Up to you to output rasters. I like to always create this, as we talked about. I just think it's good practice. And it's going to help me when I sort of create different search radiuses, which we'll see in a second, is a really important input that you need for raster. And so I'll create this called, crime dens. Maybe I'll say, 2,000. Just start big. Hopefully that'll let me save that. Cell sizes we talked about, right? It's always going to be in the units of your map. We're projected in feet. I like maybe, let's say 25. So 25 feet by 25 feet. And here, in typical ArcGIS fashion, rests the most critical field in how your density analytics will run. This determines everything, and it is hidden under a really stupid name called search radius. Right? This sort of makes it look like maybe every point is going to look around it for other points, and that's kind of true. But what it actually means is if we pretend that every point has a weight, right? For crime, it's 1. Everyone's got a point of 1. Maybe for Philadelphia blocks, it'll be the population. For the crash data, it'll be the number of crashes. Search radius tells you how far out should I be pushing that influence. And this is where you can begin to actually see concentrations at a very local level if you have a small search radius, or at a broader neighborhood level if it's wider. Now, I can't always tell you when to use each. I won't be with you for 95% of the time that you're using GIS in your life. So you need to ask yourself before you run a density operation, what kinds of concentrations am I seeking to identify? For example, if we were to do crash data, which we will do next, I probably don't care as much to see like 10, 15 block clusters of where there's crashes. I mean, that maybe tells me that a certain general area of the city has a high intensity of automobile incidents. But it would be far more useful to me, as you can sort of see coming down Broad Street here, where there are pockets of crashes, to see the clustering and intensity of crashes at maybe a intersection level or a street level. That would really help me see that here, right, this section of Broad is intensely concentrated with the number of crashes versus up here a little bit is less concentrated. It might be a little bit safer. There are sort of fewer incidences of automobile crashes happening and clustering there than there are in other parts. So that can still be a bit confusing. So let's test out a couple first so we can see the difference. So we'll start with 1,500, or maybe actually 2,000. That's what I put. So what we're saying here is that each point is going to spread its influence out 2,000 feet. And along the way, it will meet the influences of many, many other points. And you will begin to see these colorized pockets emerge that show where there's intense density across neighborhoods or across multiple blocks. Area units just helps you depict what you're going to see that returns to you. You know, when we created the LiDAR grids, the topographical surfaces came back to us with a unit of feet.
This just means if I put square miles, it's going to say the density feels like X number of crimes per square mile. But you could say X number per meter, X number per square kilometer, whatever works best for you. You don't need to focus too much on this. Densities tends to be the easier one to read. Expected counts can will produce the same relative intensity. So the colorization and the relative comparison from cell to cell will remain the same, but the number will be different, right? Whereas density tries to estimate the whatever per square mile, right? Number of crimes, population, number of crashes. Expected counts will actually try to say, all right, if we assume that there are this many actual crimes in Philly, then this cell represents X of those crimes, X total percent. So let's stick with density, just an easier one to interpret. We got our crime dense raster. We got a 25-foot cell size. We're doing our sort of search radius of 2,000. And we'll run it, let it do its thing, evaluate what comes back to us. And then we're going to run a different one on the crash data using sort of a much more granular search radius to really see how this tool differentiates depending on the sort of whether or not you want to focus at a block, at a street, or at a neighborhood level. So something comes back, looks pretty good. First thing I'm always going to say whenever we run this is ArcGIS is trying to pick the sort of best possible output for you. And, it's going to choose this symbology because this is obviously an area where there's a lot of clustering of crimes, where most of the thefts in Philadelphia occur. But you don't need to choose this as your symbology, right? You can always come into appearance, and I suggest you do this when you're creating density, and come into stretch, because stretch tends to be a really good way to visualize density. I like to do it maybe at the standard deviation. Minimum to maximum is another good way to do it. Actually, let's try minimum to maximum. Just depends how sort of intense the main point is. Now remember, that means it's stretching from the smallest value to the highest value. And then you can pick sort of a more logical color. Maybe we'll do variations on red, right? So we're scaling from a less intense red to a more intense red, and then we sort of give it a symbology here. And there we go, right? A little bit easier to sort of visualize. The same sort of patterns start to emerge, but it's a lot easier to sort of see the various concentrations of intensity than when we did the other, right? You can see sort of the intense pocket up here. Click on that. That would tell you, hey, this feels like, right, 2,700 crimes per square mile. That's sort of the intensity that you have in that area versus this, because there's so many of them clustered, that would feel like 7,300 crimes per square mile in that area. Notice, too, that the trends it's showing you are neighborhood level, right? I mean, it's showing you a large scope of an area where there's a concentration of crimes. And that's because we had that search radius of 2,000 feet. What if I do the same thing, but I make the search radius now something like 750? And I'll say that same thing, right? Crime density 750. And I'll run it, and I'll try to make sort of the symbology the same so we can see. So you'll still see areas in this part of Center City where there are a lot of sort of auto thefts and other thefts will come up as being the most intense. But you'll stop seeing these sort of neighborhood spanning points. Exactly. I could not have asked for a better outcome there, right? You start to see the mini clusters, right? The mini area here where there's a lot of crimes clustered in a 700-foot radius, and so it's intense. And you can see when these two are layered on top of each other why these 3 or 4 individual crime pockets, when looked at a larger area with a larger radius, would demonstrate this sort of neighborhood-wide concentration. But by reducing that search radius, you really get to focus in on where the tiny, sub-intense, dense clusters happen to be. So I'm going to pause this video. We'll pick up on the next one and sort of practice this again with the crash data, and then do a quick reminder on how you might convert the blocks and run density as well on those.